good afternoon to our audience in China, and a warm welcome to those joining from around the world, wherever you may be. We are delighted to have you with us for today's seminar on ocean carbon sequestration and climate resilience, part of an ongoing series endorsed by the United Nations Ocean Decade and sponsored by the Ocean Decade Program Global Ones, led by Professor Nianzhi Jiao from Xiamen University. So I'll start by welcoming everybody to introduce Professor Tim Lenton, who is the founding director of the Global Systems Institute at the University of Exeter and chair in climate change and earth system science. He will present today on this topic, tipping positive change to avoid climate tipping points. Following his presentation, we will be joined by a distinguished panel of experts for a discussion. They are Dr. Matthew England, Scientia professor at the University of New South Wales, UNSW, Australia, Dr. Stefanie Rynders, a junior scientist at the National Oceanography Centre, Southampton, UK, and Dr. Steve Sherwood, also professor at UNSW, Australia. For more detailed information on their research and accomplishments, we invite you to visit the Global One's website at www.global-ones.org. As we have only just 1 hour for both the presentation and panel discussion, we'll now just hand over to Professor Lenton without further delay. So Tim, the floor is yours. I will quit.
Thanks, Chuanlun. Great to be here at this first seminar. I'll get cracking. I want to talk about tipping positive change, or what I call positive tipping points to avoid climate tipping points. So I'm going to start with the bad news on the risks we're running with big tipping points in the climate system, but then try to cheer you up with the evidence that we're also seeing self-propelling change in the direction we need to clean technologies and zero emissions. So hopefully the whole story, we can talk afterwards about how ocean carbon sequestration can fit into this bigger picture. Let me start then with a little movie where I'm going to force a system towards a tipping point. So this is a system with a couple of alternative stable states. It's in the one in the left. It's the blue ball rolling around. This could be a bit of the climate system, subject to sort of the noise of the weather, knocking the system around, the ball around all the time. Or it could be a part of the economy and technology. But the system is being forced in a way that its state it started in is getting less stable or less resilient over time. And at some point, some amplifying feedback in the system there came to dominate and was strong enough to support a self-propelling change from one state that had lost stability into another. And that's the kind of canonical type of tipping point change. Where before it happens, some damping feedbacks in our system, whatever it is, are getting weaker. So the valley's getting shallower, and there are some early warning signals because the ball is rolling around further from the bottom of the valley as it gets shallower and it's recovering slower. And that's giving us a clue that the damping feedback gets weaker and the amplifying feedback in the system is getting stronger. And then at the tipping point there, I don't need to keep forcing the system for it to keep changing under, you might say, under its own momentum. So it's I spent about more than 20 years now with colleagues, certainly including Matt some of the time for a couple of decades, looking at what bits of the climate system could pass a tipping point due in simple terms to global warming. And these are some of those bits of the system highlighted with the sort of orange target symbols. And in the black boxes, some of the evidence we've seen over recent decade or two that change is happening in a worrying direction, and often it's a signal of accelerating change in a bad direction, which would be consistent with the possibility that these systems may be heading towards tipping points that we have other reason to think exists, partly because we've seen them tip in Earth's past, or we run our model projections of the future and we see instances of tipping points in the future projections, or our understanding of the key feedbacks tell us there could be a tipping point in these systems. I won't talk about all of them, but I'll briefly mention, we have evidence that there's accelerating mass loss from the West Antarctic and the Greenland ice sheets. And we find it hard to rule out that parts of these ice sheets might not already have passed a tipping point. You also see in the figure some arrows connecting the candidate tipping points, and that's because as scientists we got increasing amount of evidence that there are causal interactions, and unfortunately they tend to be in the direction that tipping one thing can make tipping another more likely. So we know the Arctic is warming up nearly 4 times as fast as the global average. This is clearly contributing to the accelerating melt of the Greenland ice sheet, which means that fresh water is pouring into the North Atlantic from the melting of Greenland, but also the fact that there's more rain and snowfall in simple terms in the Arctic as well, pouring out of the rivers of the Arctic. And adding fresh water to the North Atlantic is contributing to weakening this thing, the Great Atlantic Overturning Circulation, which I'll come back to in a minute, because that's crucial, because as the diagram hints, that connects up the climate system. And as that weakens and possibly collapses, it's essentially stopping a big transfer of heat across the equator from the southern hemisphere to the northern hemisphere. Leaving that heat behind is why it risks the tipping of the ice sheets of Antarctica, for example. So this is a summary of how our knowledge or our international scientific assessment of the likelihood of tipping points has changed over the last 25 years, roughly. And it's a pretty alarming figure, because when it was 2001, we, the IPCC, thought it would take 4 or 5 degrees centigrade of global warming for it to be as likely as not that we cross some big tipping points in the climate. And as of 2019, so several years ago, that had changed to realizing that we were already in the danger zone, where for some tipping points, they become as likely as not, in the range of 1.5 to 2 degrees of global warming. So that's telling us that these could be high impact, high likelihood events, not what they're traditionally thought of, which is high impact, low likelihood events. Now, we've got more detail on this now. This is from our paper in 2022, where we'd synthesized over 200 papers in the literature and made a kind of collective assessment of the uncertainty range on where the tipping point is for a whole bunch of systems down the bottom, including those Greenland and West Antarctic ice sheets and that Atlantic overturning circulation. And we made a central or best estimate of where the tipping point might be for these systems. The then current level of warming is on the bottom grey line, and you can see that some systems may already be at risk. And at 1.5 degrees of global warming, we think that, it's kind of as likely as not that you could tip, say, the long-term loss of the Greenland and West Antarctic ice sheets, which together would raise the sea level over many centuries, but in a hard-to-reverse way, by 10 meters, which is enough to flood land occupied by 1 billion people today. And incidentally, even the first meter of sea level rise is land occupied by over 250 million people. We also see directly the evidence that coral reefs are suffering widespread dieback at the moment in another record global sort of marine heat wave bleaching event, and the permafrost is already starting to thaw in an abrupt way in parts of the Arctic. So those systems are perhaps the ones at closest risk, but loads of other bits of the climate system are becoming at risk as warming increases. And if we were to continue to where current policies would take us, which is 2.7 degrees centigrade of warming later this century, then you can see how many of these systems would be at risk. including two connected things. The process of what we call deep water formation in the Labrador Sea, which is just to the southwest of Greenland. And then that plays a part or is connected to the possibility of a really big tipping point in the Atlantics. We call it meridional overturning circulation, or AMOC for short. Since 2022, I'd say the recent studies would cause us to bring the yellow color down and the dotted line down for the Atlantic tipping point, because they suggest some of our models are biased too stable, and that the evidence is this tipping point might be closer than we thought. So that one I just want to talk about briefly because it sort of has global repercussions, shall we say. So what we're talking about is this combination of the red surface water flow in the Atlantic and the blue flow is thousands of meters down, cold water flowing back southwards, and they form a kind of conveyor belt circulation that's part of this wider, pictured here, thermohaline circulation of the ocean. And this is a major redistributor of heat as well as salt around the planet, so it plays a major part in shaping the climate pretty much everywhere. And Matt can talk about deep water formation in the Southern Ocean. I just want to highlight, so I talked about the Labrador Sea, that's over here. That's one place where deep water forms in the North Atlantic. This is the other place, the sort of Greenland, Iceland, Norwegian seas. This is happening because as these surface waters in what we call the Gulf Stream here head northwards, they're losing heat to the atmosphere, so they're getting colder, and they're evaporating fresh water to the atmosphere, so they're getting saltier. And getting colder and saltier makes the water denser. It goes so dense either side of Greenland that it's an unstable situation. It's denser than the water below it, and it undergoes a process we call deep convection. It sinks from the top of the ocean to thousands of meters down. And it's that process that then supports this overturning circulation. It draws in more supply of those those dense waters. And if the deep convection or deep water formation stops, we know that there's an alternative stable state of the system where this circulation just doesn't exist. We know that because it's been tipped off and on 25 times in the last ice age, for example. But let's just get a sense of if we reach that tipping point, which can happen because of the extra fresh water that's already entering the North Atlantic region and the fact that this region is heating up. Both of those things are making the surface waters less dense and less prone to sinking, so pushing the system towards the tipping point. If the tipping point occurs, here's what it means for where I live. So this is an example where it happens at 2 degrees of global warming in actually a high resolution state-of-the-art Earth system model. This is what happens kind of to the winters in Europe. And for example, on the right, you see that sea ice extends in February down to cover, well, most of the North Sea. So much of the UK is surrounded in sea ice. This is not normal. The decadal climate extreme in London is minus 20 degrees centigrade. In Edinburgh, it's minus 30 degrees centigrade. There are 5.5 frozen months of the year in Edinburgh, 3 completely frozen months in London. And yet the summers in this tipping point world are just as hot as pretty much as they were going to be anyway, under 2 degrees of global warming. So still heat waves in London in the summer. In other words, the seasonality of the climate is just radically different to what the people of Europe are used to. So I think we would have extreme difficulty adapting to that eventual change in the climate. It doesn't unfold immediately, but once it starts to happen, the tipping point over and the change unfolds over decades, by its nature, it's hard to reverse. You may be more concerned with the global picture. So these were some fairly basic estimates of what this could do to the viable area for growing a couple of staple crops worldwide. Without going into the details, when you have this tipping point in what we call the AMOC, a number of things happen. It gets a lot drier in large crop growing regions of the Northern Hemisphere, including across Europe, and that's really bad in this case for growing crops. It also moves a band of rainfall that rings the tropics of the planet southwards. that means it's disrupting the monsoon in West Africa and in India, which is why you see a lot of purple there. It gets essentially it gets less good for crop growing because the monsoon rains are failing more often or are weaker. And in this particular simulation we looked at, it was also having a big negative impact in China, or in fact in many places. So this was a pretty striking bad example where the viable area for growing these staple crops was reduced by more than a half worldwide. And I think that would be very, let's put it simply, that would be very difficult for everybody to cope with, a kind of global food and water security crisis. So it should emphasize that we want to try and avoid that kind of tipping point. And I've already told you we can't rule out that it might happen at, say, 2 degrees of global warming. We might think it's more likely to happen at higher levels of warming for sure, but it should give us a strong reason to want collectively to limit global warming, ideally to the Paris Agreement target, which is well below 2 degrees centigrade as it's described. Now, in order to do that, we know we have to come down something like the red curve, which means we have to stop all the greenhouse gas emissions from human activities worldwide by the middle of this century. And then we need to do what you're all going to study, which is do net greenhouse gas removal in the second half of this century, whether that's with the ocean or the land or technology for direct air capture. But I'm really interested in how on earth could we believe we could accelerate change from what are currently sort of roughly stable emissions. This is just the carbon dioxide emissions, but the total emissions in carbon dioxide equivalents are roughly stable at about 55 billion tons of carbon dioxide equivalents per year, but they need to come down very sharply. And in fact, we need to be decarbonising our economy and all the activities that cause greenhouse gas emissions more than 5 times faster than we are. So my argument is that's not possible unless we believe there are tipping points in behavior and technology to clean technologies and low emission activities, where the change to those technologies and activities itself becomes self-accelerating. So that's what I've spent a couple of years in researching and writing a book about that I just published, so you can enjoy that separately. But the argument is basically, we know we're in an unsustainable state if we continue with a fossil fuel powered economy, etc. But we know there's another sustainable state of the economy that would function perfectly well, powered by renewable energy with lots of other changes linked to that, large scale electrification of the economy, changes in our diet and the associated land use and farming. And in principle, some actions could weaken the dampening feedbacks that maintain the current state, work with the amplifying feedbacks that can create change. And the concept is you could have positive tipping points from one set of technologies and behaviors to another. But I need to convince you that that's not just a cartoon, that it can happen. So I want to show first a historical example that we can change technology really quickly. This is a photograph of the Easter Day Parade on Fifth Avenue in New York City, Manhattan, in the year 1900. Everybody's out parading in their fine clothes or in the street in a horse-drawn carriage, except for one person who's in an early automobile. Can you see the early automobile? Well, I'm going to tell you it's there in the middle of the shot. But if I show you a photograph 13 years later of the same Easter Day Parade on Fifth Avenue, New York City, you have the opposite challenge in 1913 to spot the one person left in a horse-drawn carriage. They are in the same part of the street over here. But the point is, this was a rapid tipping point in personal mobility from horse-drawn carriages to cars, and there were a bunch of amplifiers that made it self-propelling. So firstly, you could say, when some people got cars, other people looked at them and went, oh, that looks good, I want one of those, which is a sort of imitation fashion craze thing. But also but they also realized, well, this may be a more convenient way of getting around and more effective. But then there are also amplifiers within technology. The more we make something, the better we get at making it. And we call that learning by doing. So then the more attractive, in this case, the car becomes as it's getting better and better, the more people who adopt it. And then economies of scale. The more we make something, the cheaper it gets to make the next unit. And that was very true for early cars. The Model T Ford came onto the market costing over $900, and just within less than a decade, the same Model T Ford cost less than $300. So that's a huge amplifier of uptake. It's making it more accessible to more and more people to consume. And then there's something I call technology reinforcement. You know, when a new technology emerges, other technologies emerge that make it more useful, or technologies get put together. So in this case, you know, no point having a car if you haven't got a gas station to fuel it in. But gas stations arose, and roads also arose to drive around on. But also, early cars needed crank starting if they were gasoline cars. But after a few years, somebody worked out we could put an electric starter motor on the car. Then you remove the inconvenience of crank starting, and it makes it a more convenient vehicle, and that boosted the uptake. This happens across technologies. They follow the car is shown here on the left-hand one, but loads of technologies follow these S-curves, they're called, a phase of exponential growth and then very sharp, sustained uptake. And then they saturate as everybody basically adopts them. And that's even true for infrastructure like railways or whatever. But this is because of the amplifying feedbacks that really create the accelerating change in the early S-curve phase. And they're happening now for the clean technologies we need. So this is the example of Norway because it's led the world in the uptake of electric vehicles. And this matters because road transport's responsible for about 14% of greenhouse gas emissions. It's dominated by cars, but there's also a chunk from trucks, which is about 3 or 4% of greenhouse gas emissions. And you see here the Norwegian market tipping in an S-curve quite abruptly from petrol and diesel cars to battery electric and other electric vehicles. And now the market share for battery electric in Norway is at about 95%. Of course, the Chinese market is also tipping to electric vehicles, and there's a massive market. And the crucial story here is the more electric vehicles that get adopted worldwide, the cheaper and the better they get. Principally, it's the battery that was adding to the cost of the vehicle, but the dotted lines here on the left axis show how the price of the batteries has plummeted as the fleet of electric vehicles worldwide, the numbers being made and sold, has grown exponentially in the stacked bar chart. In fact, the batteries come down in price nearly a factor of 10 in a decade, which is spectacular. And also the range you can get from a given battery has gone up by a factor of nearly 3 in a decade, which is just phenomenal. And the point is they continue to get cheaper and better, the batteries and then the overall technology of the electric vehicle, which would explain why the total number of vehicles is on exponential growth. It's doubling every year and a half. And the batteries plummeted like 30% in price in China last year and 20% across global markets. So that's a really strong amplifier, which brings in sequence a bunch of markets to the tipping point where electric vehicles are cheaper to buy than petrol or diesel ones, and then everyone will adopt them. In Norway, I won't tell you the whole story, but there were a bunch of progressive policies that brought forward the tipping point, and that's of course also been true in China. But once you get to the point where the batteries have got cheap enough, you don't need policy support. As I said, this will become the cheapest and the better technology, and people then will choose it. And at that point, you have several other possibilities. So you're tipping. The electric vehicle tipping point is already spreading across major markets. But that means just batteries are getting cheaper and cheaper all the time. And batteries are useful for other things, not least for electrifying goods transport, like trucks, for example. And again, China's leading the world in getting towards the tipping point to electric trucking. The fact that the markets are tipping to electric vehicles is taking away the main demand for oil in the global economy. So it's also going to be causing oil firms to start thinking about their future, and pension funds thinking about whether they want to stay invested in oil and so on and so forth. But cheap batteries is also really important for an even bigger tipping point, which is the one from fossil fuel electricity generation to renewable power. And that's because if we imagine a future electrified economy supported by renewable energy for the most part, well, you have to balance electricity supply and demand. And when you're demanding electricity to boil the kettle, watch the television, the sun isn't always shining and the wind isn't always blowing. So you need cheap electricity storage on the grid, and that's going to come overwhelmingly from batteries, which come from a sector that demands more of them, namely road transport. And that means actually there's a massive supply of cheap batteries to support renewable electricity on the grid. So I'm going to to finish with the big tipping point to renewable energy. I'm back in the UK here, which is a bit of a small country, but it's important just to show how an example again of how there's been a big tipping point in this case in power generation in the UK. The black line is our electricity supply in the UK from coal burning. It was at 40% of our power supply in 2012, and it fell off a cliff. And now there's also been exponential growth of renewables in the yellow, blue, and green, and now renewables are giving us the 40% of power we used to get from coal about a decade ago. What happened here was some policy, but it was just to put a modest price on carbon emissions just in the power sector in the UK. But the government promised they were only ever going to increase that, what they call floor price on carbon. And at some point in 2013-14, that just made the economics of coal burning not very profitable because it's the dirtiest form of power generation. And that meant investors started pulling their money out of coal burning and putting it into renewables or gas or whatever else. And that made it even less economic to burn coal. So even more investors pulled their money out, and you had this tipping point away from coal power to clean power. And it became irreversible because utility companies were left with power stations doing nothing. And they thought, well, this is costing us money, and they had to destroy them. And this is one in Oxfordshire being destroyed. Now, I realize, for example, in China, that you have growing electricity demand and you have had growth of both coal power and solar power. But now the solar power growth was phenomenal last year. And I would predict that this year it may well outstrip the growth in electricity demand. So China, for example, is very close to the point where it will start closing coal power stations. India will need to follow, but we see the trend in the right direction. And it's all supported, the rush to renewables, by the fact that they're the cheapest form of electricity generation now. This is a famous curve for solar panels showing how they get cheaper the more that are deployed worldwide. It's a log graph. But the story is, for every doubling in installed capacity of solar panels worldwide, the price comes down by a quarter. Sometimes it comes down even faster, like from 2008 to 2018, and it's continuing to come down. And this is giving us the cheapest electricity ever in history. And China is the country that's dominating the rollout of this technology at the moment, but it's spreading worldwide. And wind power is also getting cheaper the more we deploy it, but solar power is getting cheaper faster, if you like, which is why our state-of-the-art model projections, led by Femke Neisser, show that as you go through the rest of this decade, solar comes to dominate as the cheapest source of power, together with battery storage, in almost all the world, with a few countries very windy countries where wind stays in the lead. So we predict that we're already past the tipping point, actually, where solar and wind are destined to dominate future electricity supply, but we can still have policies that make that tipping point spread faster and the transition go faster. So to finish up, we have like a model of 72 world regions and several sectors of the economy, including the power sector, cars, trucks, heating and cooling our homes. So it's a data calibrated model for the 72 world markets. And recently we just started modeling the coupling between sectors, like the fact that the cheap batteries were coming kind of either from second hand out of cars onto the grid, or cars are being plugged into the grid for electricity storage and grid vehicle to grid connection. So there's a link there. But then as electricity gets cheaper, it's incentivizing electrifying transport, because it's even cheaper to run around in your electric vehicle or in your electric truck, or to have an electric heat pump to heat your home. So we've been modeling out the feedbacks between sectors of the economy, and then we can look at what are the most effective policies to bring forward the positive tipping points in the different sectors. So there's a lot of information here, but basically the power sector is the top line. The heating home sector is the next line. Cars is the third line. Trucks is the fourth line. Green or yellow and blue at the top indicate the clean technologies. And the columns are showing on the left where will we go with current policies, and we see that we're seeing the rise of renewable power anyway. But then what happens with different policy options? And I'm interested particularly in the last column, which shows that for the sectors that are struggling to reach the tipping point, like trucking at the bottom, or to a degree electrifying cars or heating, the way that the most powerful policies to activate amplifying feedbacks that I talked about, learning by doing economies of scale, bring down the price, improve the quality of the clean alternative, the most effective policies are the ones where governments mandate the phase in of the clean technology and the phase out of the fossil fuel one. So it's like, for example, in Europe, we have a ban on the sale of petrol and diesel cars from 2035 onwards. In the UK, it's actually 2030. That is those kind of policies are by far the most effective ones to bring forward the positive tipping points that can have a huge impact on decarbonising the economy. So I'm through my 30 minutes, and luckily I'm on the summary, which is I've shown you, and the others will be able to talk about this even more, that we're already at risk of crossing really, I would call, dangerous tipping points in the climate, and basically every fraction of warming increases that risk. I tried to explain that to limit that risk from the climate tipping points, we have to aim to limit global warming well below 2 degrees centigrade. And that's not going to happen now if we carry on the trajectory we're on. It really needs positive tipping points of accelerating transformative change in the major sectors and markets in the economy. But I've tried to show you that that's already happening, and I'll tell you a bit about the policy actions and the amplifying feedbacks in society and technology that can actually bring forward these positive tipping points to avoid the climate tipping points. So thanks very much.
Thank you so much, Tim, for an excellent presentation. Very insightful, very impactful. It's really an eye-opener for me, your presentation, because I originally thought your talk would be just focusing on climate change, and now you actually touched on, turning points, tipping points for industry, for society. That's really incredible. And now let's move on to our panel discussion as we planned. Again, joining us are Drs. Matthew England and Dr. Steve Sherwood from the same institution in Australia, UNSW, Dr. Stefanie Rynders from Southampton, UK. I really like we invite you three to join to this panel because I read Tim's the huge document, the global tipping point, the document that involves close to 200 people, and you three are outstanding scientists in that document and with the different backgrounds. So I really like to have you all to engage into this discussion from your own expertise, from your own field. So the first question is really how you have involved in that document, contributed to that grand outcome. I would like to start with Matthew, Dr. England, with your expertise really related to circulation, large-scale ocean circulation, and its influence on regional and global climate. And Tim's presentation really start big. Everything, all the tipping points are large scales. So Matt, can you share your insight, your contribution to that document, and from your own expertise in your field?
Yeah, thank you for the opportunity. Thanks for joining everybody, and thank you, Tim, for your presentation. Outstanding to see this overview. And as Tim mentioned during the talk, and as per your introduction just now, my expertise is in ocean circulation, and ocean circulation tipping points was the contribution I made to this report. One of the things that I've tried to do over the last couple of years is to raise the profile of the younger brother or cousin or sister of the North Atlantic overturning, and that is the Antarctic overturning. It's a really interesting overturning circulation off Antarctica. It also involves the formation of dense water, but this water is even denser than the water that forms in the North Atlantic. It flows into the ocean abyss. Climatically, it's not as important as the Atlantic overturning because the Atlantic overturning brings a lot of heat towards the North Atlantic and affects climate in the ways that Tim described. The Antarctic overturning doesn't do that to the same magnitude as the North Atlantic, but what it does do is it actually recirculates the abyssal ocean nutrients. So when biological matter dies in the upper ocean, it sinks to the ocean abyss, and so we have very nutrient-rich water right at the bottom of the ocean. And unfortunately, we're seeing signs that this overturning circulation has already slowed down by about 30%. And the projections we've run are that slowdown will continue. And unless we reduce emissions of greenhouse gases, it looks to me to be virtually certain that circulation will slow down over the coming century or so. And if that happens, we won't see this recirculation of nutrients back up to the surface, which would have big impacts on our biological cycles in the upper ocean, which can in turn, unfortunately, again, as Tim outlined, it can have a cascading impact because that overturning circulation off Antarctica draws down carbon. And so if we cut it off, we actually cut off a way that the ocean absorbs carbon for us, kind of free of charge, except for acidification. And so, yeah, that's a long way of answering your question. My main input to this report was around this overturning circulation, both the North Atlantic, because I'm also interested in that overturning, but also this overturning off Antarctica.
Thank you so much, Matt. I'd like to let Stefanie to add to what Matt says about the overturning from your perspective, being a modeler focusing on Arctic work, and Tim's presentation really mentioned the two big turning points associated with polar ice melting. How would the circulation be related to the polar region? Stefanie, can you please follow up on that?
Hello, everyone. I guess first to answer which bits I've been involved in, maybe. So in the first tipping points report, I was part of this ocean atmosphere circulation, so I guess the same as Matt. But also I've been part of some of the governance section that looking at cascading tipping points between different climate components, but then also like impact on socioeconomic components, which is quite interesting. And I think for the current, the next version of the report, which we're writing at the moment, I'm part of
this is a
case study on AMOC.
Okay, so it's version 2?
Yeah, there is a new version coming up.
Okay.
I didn't
All right.
give too much away, but yeah, and then I'm also again taking part in some of the government section this time is on talking about different actors and their role in managing tipping points. So for the polar regions wise, so actually I think in this version we concluded that sea ice is probably not actually a tipping point. At least summer sea ice is not. Winter we don't really know. because of, especially in summer, because of lack of some self-reinforcing mechanisms. However, there is certainly potential for rapid change in tipping points, which is maybe in practice almost the same thing, but not quite as bad because it's more reversible. So yeah, and the reason why it can happen is basically because for heat influx may be most in the North Atlantic. So that is really what drives sea ice to really melt, and which can happen fast. But also, if in the future the heat influx from the North Atlantic should decrease, then actually sea ice can also grow back.
All right, thanks so much, Stefanie. So we talked about the water, we talked about the ice. Now let's go to the air, the climate, and let's welcome Dr. Steve Sherwood. Steve, to tell from your perspective how clouds and water vapor be related to the tipping point.
So I was also asked to contribute to the atmosphere ocean part of Tim's assessment by Sina Loriani, who I think deserves a shout out because did a fantastic job in herding us all and getting it and putting our part together. I didn't do a huge amount of work for this fine document, but yeah, I also want to say I really appreciated, Tim, your presentation. I think that we need to do more of presenting the positive, these things that are happening, and it's just an example of how something can be happening around you and you not see it because you're focused on something else. So I'm really happy that you showed that, but that's not what any of us worked on in the report. We were all looking at the bad stuff, and and some of the worst stuff you could imagine, which people worried about a lot in the older days, was the possibility of the planet ending a greenhouse runaway. Where it could just turn into Venus or something. And so I thought that we should have a little section of this report that starts from that, but also discusses more generally what do we know about cloud and water vapor changes, and is there any possibility? And this is kind of a outside of the box, thing, which I do think we need to think about when we're thinking about climate change. We need to think about not only the tipping systems that we've known about forever, like the AMOC, but also things that we might not have thought about, or that might have only been thought about in the back of dusty rooms somewhere. So we looked at that, and I think if you look at the literature and understanding, there's really no chance of a runaway where the climate becomes stable, which is great news. But there is some work suggesting the possibility of rapid changes in low cloud cover. And so I would, I think looking at the whole body of literature, it doesn't look too likely, but it's a possibility. And I think our limitations and ability to model the system or have the kind of observations that you would need. We don't have paleo observations of cloud cover, for example. So it's really hard to rule these things out. But we decided it didn't look too likely. And then the other sorts of things that have been suggested is the possibility of a reorganization of the tropical circulation by an enhancement of something called the Madden-Julian oscillation. And there is evidence that could intensify, or at least that the rainfall associated will probably intensify in a warmer climate. But again, it's not too likely that it would actually rearrange the circulation. So I wouldn't say that we discovered any obvious scary things, but definitely some things to think about and incentives to try to model the system better, because I think there's really some limitations, not only in clouds, also in other aspects of the system, things like Amazon, dieback and so on, where it's possible that all of our models are doing the wrong thing.
Thank you so much, Steve, for all three very insightful comments or add-on to Tim's presentation. Since Tim already let us know he is leading maybe another big team to work on GTP version 2. So maybe we can discuss a little bit why that's urgent for Tim to come with version 2, and how you three maybe adding to the next version. If you want to see that next version, what will be your new highlight? Tim, can you please tell us why is it urgent to have a version 2 document?
For sure. Yeah, absolutely. Well, first I should also say this is a team effort. I mean, I'm just like the person trying to hold it together and edit. So like my debt of gratitude goes to well over 200 authors the first time around, including Matt, Stefanie, and Steve. It wouldn't happen without us as a community kind of pooling our knowledge and like interrogating each other, and that's the way the science happens. You know, you keep each other honest and learn from each other.
Right.
And the reason we would do it again after 2 years is, well, principally because the climate is changing quite fast in some aspects, and science is also evolving quite fast and telling us new things all the time. That's also true on the other side with the positive tipping points. You know, there's been really significant change in major sectors and markets in 2 years. And basically, I don't know about the other three, but my inbox is absolutely full of people who want to know more, both about the profound risks from the Earth system tipping points, also the opportunities from the positive tipping points, and also in the middle, how on earth do we govern all of this? So what we've tried to do, what we feel that, you know, I suspect all four of us are in various ways now or in the past contributors to the Intergovernmental Panel on Climate Change reports.
Right.
I'm a lead author for the next one and for the chapter that's going to come on tipping points. But I don't want to have to wait till like 2028 to like share our synthesis of the literature, which will be cut off before that on this knowledge, because people want a regular update. So that's sort of, we're trying to fill, I suppose, that demand for, you know, okay, what's changed? What's changed even in 2 years? And there's been, as I think, you know, others on the panel can speak even more on this than I can, but we've just been through nearly 2 years of unprecedented anomalies in sea surface temperatures and associated global atmospheric temperatures, and we're still as a community trying to puzzle out quite what was going on there, quite what the reasons behind such a large and persistent temperature anomaly have been. So that sets part of the climate context, and it's then linked to the fact that we get new, in this case, negative insights, like all our coral reef experts in the coral reef case study that we're going to release in a month are telling us the coral reefs basically are past the tipping point from excessive heat, and we now have to kind of I suppose we now have to think about, well, what can we do in a situation where many of them are going to be in a kind of tipped state. So yeah, that's the short. There's a lot more to say, but I'll let the others come in as well, because it's clear to me that the systems that we study as scientists are changing fast, and we've got new knowledge on that, and it's clear that there's a big audience out there who want to have that some of that new learning and evidence translated for them.
Thank you so much, Tim, for the insight on the next edition. I'd really like to hear Steve to follow up on this, climate 2 degree, the critical point. So what's the IPCC's attitude now? Are we still holding on at the 2 degree or we have passed it? Steve, since you also involved with,
I can't really speak for the IPCC.
Yeah.
I mean, I think there's the growing feeling that 1.5 is gone, but 2 is still attainable, but certainly not easy. The Australian government just released a report on Monday. This has gotten a lot of fanfare. It's our first national climate assessment, and they looked at 2 degrees and 3 degrees. So they're already thinking 3 degrees is a possible scenario that they need to look at. So this is an evolving target, unfortunately. I think
one of the things I like to follow up with that. You know, people sometimes get disenchanted and they think, well, we've lost the battle. We should sort of, they almost want to give up. And I think, it's not like we have these increments of a full half degree Celsius. Every fraction of a degree Celsius we can save it, as Tim's graph showed. The tipping points thresholds, they're not going to be in whole degree numbers, and we've got to really, whilst we probably have lost the chance to get to 1.5 degrees Celsius, 1.7, 1.8 is a way better world to be in than 2 degrees. And we've got to really aggressively, again, the tipping points that are positive that Tim outlined are just so encouraging. The fact we've got these societal tipping points where, we hope that the wheels fall off the fossil fuel sector and we see stranded assets. That's the best outcome to secure a safer climate future. And so it's really encouraging to see that we have these societal tipping points that can work in our favor, to see climate change, dealt with.
I think I may be slightly more optimistic, so to say, but I think well, if you look from the, let's say, the energy system point of view, and also there are many people making prediction of emissions as well. It's not just like as natural scientists make prediction of what happens to the climate system, and actually those predictions, like each time when there are updates, even either the, say, maximum, like the peak, either stays the same or it goes down. Like so, our emission reduction, let's say that, like the transition to the low carbon future is actually speeding up compared to predictions that happened before. And actually, some of the reports that people use quite often, like from the International Energy Agency, they also make a prediction each year of what may happen in terms of emissions and what the resulting temperature will be. They've actually had a very long history of always underestimating the speed of the expansion of renewable energies.
Right.
So actually, but if they say, I think the current prediction may be something around 2.7 or something, but actually those are probably a bit too high than what is actually happening at the moment.
Thank you for this wonderful presentation and discussion. Now, I do say we need to take a few questions from the audience, and I communicated with Tim beforehand about some undergraduate students. They did some homework. We give them a couple of assignments to let them to read the big document and come up with some questions. And who answered those questions? DeepSeek. So I'll show you a couple of slides, and Tim, you guys can judge whether the questions are correctly answered by DeepSeek or other AI technology. So everybody, and Tim, this is the question asked by one of the undergraduate students at Xiamen University. It says, for large and complex real-world Earth systems like the Amazon rainforest on the Greenland ice sheet, how can we effectively extract reliable early warning signals from observational data full of noise and natural uncertainties? And DeepSeek answered with the following: spatial temporal filtering, multi-proxy synthesis, and detrended fluctuation analysis, DFA. So Tim, this is a question to you also.
Yeah, I mean, DeepSeek isn't doing a bad job here, and you'd hope it would be pretty good if it's kind of got the report and the corpus of the literature in its learning. I tried to show right at the start of my talk, I was showing you the ball rolling around in an ever shallower valley. And that already shows you visually that there are telltale signs before the tipping point that even if the noise in the system that's nudging the ball stays exactly the same, as the valley gets shallower, the ball's going to roll away further sideways and it's going to roll back slower. And that gives us already some statistical signals we can look for. So DeepSeek gives a rather kind of Well, not a super clear answer. Hopefully the four of us could do a bit better in terms of just explaining the core principles, but it hints at the underlying understanding. But this is, of course, the thing. Humans, thankfully, are still a little bit ahead in understanding and explaining the fundamental principles, but DeepSeek has spotted that yes, you can look at lag1 temporal autocorrelation to look for this signal. In fact, what it isn't telling you is what, of course, you could ask it what the limitations are of these methods and so on. But I think we're all, as scientists, involved to varying degrees, also in trying to predict when these big tipping points will happen, and this is one way to do it. And of course, building like a process-based model that we trust is the other way we do it.
Right. So in other words, basically, if the students go to DeepSeek, get some answers, pretty much they can trust the answer from DeepSeek.
I would urge the students. Well, they could broadly. This answer is not bad, but I would urge the students to understand the underlying principles and, in fact, mathematics, which DeepSeek is not doing. Doing.
Yeah.
Because then you'll actually understand how to address the problem.
Right. Okay. So basically, that's just one of the examples for AI technology to help student learning. At SysTech, we just had a seminar yesterday to expand AI learning into every classroom. I wonder whether you guys are using AI to help you with your teaching in your classroom on topics like this. I mean, do you guys feel comfortable using AI to invade your classroom?
Yes and no. I mean, we try to encourage the students to think critically for themselves. They maybe get a start. I think, as Tim outlined just then, maybe you get a start on an idea or two. But actually, and for the mathematical courses, we really want the old school approach of pen and paper and deriving things, because nothing beats that engagement of a student's brain in the activity. But it's a new tool that's definitely useful. And I mean, it's great to, a new paper comes out, you can get a couple of paragraph summary if you're in a rush rather than reading it cover to cover. Why not? But it needs to be used carefully for sure.
Sure. Be careful.
And what I didn't tell you is we do use it in research. And in fact, my group and collaborators have been training a particular couple of deep learning architectures to look for these early warning signals of tipping points, because you can train them on a massive set of instances from simplified models.
Also, another purpose of this seminar series is really to stimulate the community to engage in science publication, in dissemination. We are in the process of working with Nature publications, Nature Geosciences. And one recommendation maybe we can have a summary of questions and answers that can be linked to the journal's perspectives or highlights. So you guys are welcome to contribute to any topics. I'll follow up with the Nature journals publishers to have a collection on this topic. So again, thank you all very much. Thank you, Tim, Matt, Steve, and Stefanie, for a wonderful presentation, wonderful discussion. Thank you all so much.
Thanks, everybody.
Okay, good day.
Bye-bye.
Bye.
Bye.
Bye.